There was a time when Earth did not resemble a planet we would recognize. There were no oceans, no continents, no breathable air. The surface was hot enough to glow. This was the Hadean Era. More than 4.5 billion years ago, Earth was still forming. It gathered from dust and shattered stone within a turbulent disk encircling a young sun. Collisions were constant. The sun itself shone dimmer than it does today, yet the planet below remained unbearably hot. Collisions were constant. Each impact added mass and released extraordinary energy. Temperatures at the surface likely rose beyond 2000 degrees Celsius, enough to melt nearly every mineral into a global ocean of magma. Heavy metals sank toward a forming core, while lighter materials drifted upward. The planet separated into layers as radioactive decay and gravitational compression continued reshaping its interior. Deep below, the earliest beginnings of a magnetic shield may have stirred, while above the sky was thick with carbon dioxide, methane, nitrogen, and vaporized rock. Then something struck. A body the size of Mars collided with Earth, transforming it completely. The crust vaporized, debris escaped into orbit, and slowly gathered into the moon, which once loomed far closer and far larger in the sky. Earth rotated faster then. Its days were shorter. Its surface may have liquefied again from edge to edge. Asteroids continued to fall. Some released more energy than all nuclear weapons ever built combined. Any fragile crust that formed was fractured and recycled back into magma. Almost no rock from those first 500 million years survives, and yet tiny zircon crystals suggest liquid water appeared astonishingly early. Chemical traces hint that life may have begun during or shortly after this chaos, which raises questions that are still debated today. How did Earth transition from molten rock to stable oceans? How could water exist while impacts still scarred the surface? What conditions allowed chemistry to organize itself into something more? And why did this unstable beginning not prevent life from emerging later? Tonight, we step back to the earliest chapter of our planet's story. But before we begin, if you enjoy these gentle journeys into Earth's distant past, I'd love it if you gave this one a like and maybe tapped subscribe. It helps more curious minds find their way to this corner of the internet. And if you're still awake enough to type, let me know in the comments where you're listening from and what time it is where you are. It's always a joy to see how far across the world this little corner of science travels. Now take a deep breath, let your shoulders soften, close your eyes if you'd like, and together, let's go back to the time when hell was still on Earth. Before there was a planet, there was only a thinning veil of dust suspended in a widening disk around a young and restless sun. The particles were small beyond imagination, mineral fragments and frozen grains adrift in slow orbit, each following gravity's quiet insistence. What began as gentle attraction gradually deepened into motion, and motion gathered into collision. The solar nebula did not ignite in a single burst, but tightened inward over long spans of time, its central star brightening while the surrounding disk thickened into lanes of debris that circled with increasing velocity. Within that churning ring, dust met dust. Static charges allowed the smallest fragments to cling together, forming clumps no larger than pebbles. Pebbles struck other pebbles and fused into stones. Stones collided and fractured, then reassembled in the same restless sweep. Accretion was not orderly. It was a patient accumulation guided by countless impacts. Each union increased mass, and with mass came stronger gravity. Objects grew from meters to kilometers, from scattered fragments into solid bodies that dominated their local regions. These early planetesimals did not drift peacefully. Their paths crossed and recrossed, and every crossing held the possibility of sudden transformation. Collisions released immense energy. When two bodies met at high velocity, their kinetic force converted to heat, and stone flared white at the point of contact. Some impacts were glancing, reshaping surfaces, and scattering debris back into orbit. Others were direct and devastating, shattering entire bodies into glowing fragments. The region that would become Earth experienced this bombardment repeatedly. As mass accumulated, gravitational compression intensified. The weight of newly gathered material pressed inward, converting potential energy into internal heat. At the same time, unstable radioactive isotopes embedded within the forming planet decayed, releasing further energy deep below the surface. The young Earth grew not as a cool sphere, but as a furnace. With each major impact, its outer layers softened, then liquefied. Material sank and swirled. Molten rock pooled and flowed, unable to retain a stable crust. The heat became so pervasive that differentiation began almost immediately. In this partially molten world, elements did not remain evenly mixed. Heavier metals such as iron and nickel, drawn by gravity, migrated downward through the silicate melt. They gathered in descending currents, coalescing into larger masses that plunged toward the center. Lighter minerals rose in response, forming an early mantle of buoyant rock above the metallic descent. This separation was not merely structural, it reshaped the planet's future. As iron accumulated in the deep interior, it formed a dense core that retained extraordinary heat. Convection currents stirred within the molten metal, driven by temperature differences and the slow crystallization of inner layers. These movements, though hidden far below any surface, laid the groundwork for a magnetic field. Even in its infancy, Earth was beginning to generate an invisible shield, subtle at first, but destined to influence everything that followed. Above this reorganizing interior, the surface remained volatile. Impacts did not cease once a threshold size was reached. Instead, the growing planet drew in even more material, its gravitational pull strengthening with every addition. Massive collisions remelted vast regions, blending newly arrived material into the incandescent whole. The forming Earth was a dynamic equilibrium between assembly and destruction, each impact both building and erasing. Through this relentless cycle, mass increased and structure clarified. A core settled at the center, a mantle thickened above it, and the earliest hints of crust attempted to form along cooling margins before being swallowed again by heat. From drifting dust to molten sphere, the transformation unfolded through gravity's steady command and fire born of motion. The planet did not emerge gently. It condensed out of chaos, shaped by energy that both threatened and defined it. Within that crucible, the essential architecture of Earth took shape, a layered world forged from collisions and guided by forces that continued long after the disk itself began to thin. There was a moment in Earth's early existence when its growing mass met something nearly its equal, not as scattered fragments this time, but as a world in its own right. The encounter did not arrive gently. It emerged from an intersecting orbit, a protoplanet moving through the same young solar system, bound by gravity, yet set on a fatal crossing. Scientists call this lost body Thea, a name carried from myth, though its presence is traced not by legend, but by physics and stone. The collision unfolded at extraordinary speed. Models suggest that Thea may have been roughly the size of Mars, its mass enough to challenge the planet, still assembling at the Sun's third orbit. When the two bodies met, their outer layers did not shatter into cold fragments. Instead, rock behaved like fluid under the force of impact. Shock waves rippled through both worlds, compressing and heating matter to such extremes that crust and mantle were stripped away, vaporized, and flung outward in incandescent plumes. The newly differentiated layers of early Earth were disrupted. iron already nested toward its center, while silicate mantle surged upward and outward under violent acceleration. Much of Thea's metallic core is thought to have merged with Earth's own, deepening the planet's iron heart. This conclusion arises from subtle evidence preserved in lunar rock. Samples brought back during the Apollo missions revealed something remarkable. The isotopic composition of oxygen within lunar basalts mirrors that of Earth with striking precision. Oxygen isotopes act like fingerprints formed during planetary birth, and the close match suggests a shared origin rather than the capture of an unrelated body. The moon does not carry an entirely separate signature. It appears to have been fashioned largely from the outer layers of Earth itself, blended with fragments of Thea and lifted into orbit by unimaginable force. In the immediate aftermath, Earth did not settle. The energy released was sufficient to liquefy vast regions once more, remelting any crust that had begun to stabilize. A global ocean of magma likely resurfaced the planet, glowing beneath a thick atmosphere of silicate vapor and volatile gases. Above this incandescent sphere, debris did not disperse into the dark. Gravity gathered it into a dense ring encircling the planet, a shimmering arc composed of molten droplets and vaporized stone. Within this ring, collisions continued, though at lower velocities. Particles clumped together, merging through mutual attraction and gradual cooling. Over time, the fragments coalesced into a single dominant body, its mass increasing until it cleared much of the surrounding debris. The newborn moon orbited far closer than today, looming large in Earth's sky. Tidal forces between the two bodies were immense, their gravitational interaction transferring angular momentum from Earth's rapid rotation to the expanding lunar orbit. In those early days, Earth spun faster, but the presence of its companion began to regulate that motion. As the moon drifted gradually outward, it exerted a stabilizing influence on the planet's axial tilt. Without such stabilization, simulations suggest that Earth's obliquity might have varied chaotically over geologic time, leading to extreme climatic swings. Instead, the tilt settled into a relatively narrow range, permitting seasonal rhythms that remained consistent across ages. The moon-forming catastrophe reshaped more than the planet's surface. It altered internal dynamics, deepened the core, and forged a partnership between two bodies whose gravitational dialogue continues. From a collision that could have ended planetary coherence emerged a system bound together by shared material and balanced motion. The violence was profound, yet within its aftermath lay a new equilibrium, one that would quietly govern tides, rotation, and orientation for billions of years to follow. Long before any surface could endure the weight of rain or stone, Earth carried its history in a mineral no larger than a grain of sand. Zircon crystals, resilient and nearly indestructible, survived where landscapes did not. Within their atomic structure, ratios of uranium and lead mark the passage of time, and isotopes of oxygen whisper of the conditions under which they formed. Some of these zircons, discovered in ancient terrains of Western Australia, date back more than 4.3 billion years. Their chemistry suggests interaction with liquid water and cooler crust, yet they also imply an earlier phase when the planet was dominated by something far more molten. Planetary models, informed by thermodynamics and impact simulations, indicate that after the great collisions of formation and the rearrangements that followed, Earth's outer layers existed as a vast ocean of magma. This was not a shallow sea, but a global shell of molten silicate extending perhaps hundreds of kilometers deep. In such a state, convection churned continuously. Hot material from below rose toward the surface, cooled slightly, then sank again in slow, overturning currents. The planet radiated energy into space, yet the depth of melt ensured that solidification could not occur instantly. Cooling required time measured in millions of years, and during that span the surface would have resembled a restless, incandescent expanse. The color of that surface likely shifted with temperature. At extreme heat, molten rock emits light, first dull red, then brighter hues as temperatures climb. Calculations of early thermal conditions suggest that vast regions glowed steadily, not from flames, but from their own heat. There were no stable mountains or basins, only a shifting crust that attempted to crystallize along the uppermost boundary before being drawn back down into softer layers below. Crystals formed and dissolved in cycles, their brief existence part of a planetary heartbeat that pulsed beneath a heavy sky. As this magma ocean convected, it also breathed. Dissolved gases trapped within molten rock gradually escaped through degassing. Water vapor, carbon dioxide, nitrogen, and trace compounds separated from the melt and rose upward, thickening the primitive atmosphere. Instead of a clear boundary between solid ground and air, there was a gradual exchange, a boundary layer where vapor condensed and returned as droplets, only to be heated again from below. Volcanic plumes were not isolated events but expressions of a planet-wide process of release. Each bubble that reached the surface carried material from deep within, contributing to an atmosphere that grew denser as cooling progressed. Cooling itself unfolded unevenly. Regions exposed longer to space began forming a thin, solid lid, a proto-crust composed of lighter minerals crystallizing from the melt. This crust was fragile at first, fractured by ongoing convection beneath. Some areas thickened enough to remain stable for extended periods, while others were recycled downward. Zircon crystals record this interplay, preserving evidence that liquid water may have briefly contacted these early solid patches, altering their chemistry before renewed melting erased most traces. Over time, the depth of molten material decreased. Heat radiated away more efficiently as the surface area stabilized and the frequency of catastrophic remelting events lessened. The transition from fully molten to partially solid did not occur in a single threshold, but through gradual stiffening, semi-solid layers accumulated, forming a more durable outer shell. Beneath it, residual melt continued to circulate, but the balance shifted. The planet moved from a glowing ocean of rock toward a world capable of sustaining a lasting crust, one crystal lattice at a time, the memory of fire slowly giving way to the first hints of permanence. For a brief interval in the planet's early cooling, a thin skin began to gather at the surface, fragile yet persistent. It did not arrive as a continent or a stable horizon, but as scattered rafts of solid mineral forming atop a restless interior. As heat escaped into space and convection slowed near the boundary, crystals locked together into a coherent layer. Feldspar, quartz, and other light silicates crystallized first, assembling into buoyant patches that floated upon the denser material below. This was the earliest crust, delicate and uneven, fractured almost as quickly as it formed. Beneath that new surface, heat continued to circulate through a mantle still carrying the memory of deeper fire. The crust was thin compared to what would exist billions of years later, and it flexed under internal motion. Yet it was real, a transition from purely molten terrain to something capable of resisting deformation for a time. In isolated regions, these protocontinents may have cooled enough to host surface water, allowing liquid to pool in shallow depressions and interact with fresh rock. Chemical reactions etched subtle signatures into minerals, altering their isotopic ratios in ways that could endure even if the surrounding landscape did not. Stability remained provisional. Large bodies still moved through near space, remnants of planetary formation whose paths occasionally intersected Earth's orbit. When massive impactors struck, The energy released did more than scar the surface. Shock waves fractured crust into fragments, while intense heat locally remelted both target rock and incoming material. Some collisions were powerful enough to liquefy vast regions, sending broken plates of early crust downward, where they dissolved back into magma. Recycling became a defining process. Surface rock, newly solidified and briefly weathered, returned to the mantle in a matter of millions of years. This relentless overturning explains why almost no intact Hadean crust survives today. The geological record from that era is not missing by accident, but by design. Plate tectonics, which would later shuffle continents across the globe, had not yet settled into its familiar rhythm, yet vertical recycling operated through gravitational instability and impact-induced melting. Denser materials sank, lighter materials resurfaced. Each cycle blurred the boundary between surface and interior, erasing landscapes before they could mature. By the time Earth entered a more stable epoch, the earliest crust had been almost entirely consumed. And yet, not everything was lost. Within ancient sedimentary rocks of Western Australia lie zircon crystals older than any known outcrop. These zircons did not survive as part of their original crust, but as resistant grains, transported, buried, and preserved within younger formations. Their uranium to lead decay ratios indicate ages exceeding 4 billion years. Even more revealing are their oxygen isotopes, which suggest that the rocks from which they crystallized had interacted with liquid water at relatively moderate temperatures. Such evidence implies that parts of the early crust cooled enough for water to circulate through them before later destruction. These crystals function as time capsules, carrying a geochemical memory through cycles of melting and deformation. They reveal that early crust was not uniformly infernal, but experienced intervals of cooling sufficient for complex processes to occur. Solid rock formed, fractured, altered, and descended, yet its remnants linger in microscopic form. The first crust did not endure as landscapes or mountains, but as mineral witnesses embedded within younger stones. Through them, the fleeting solidity of that ancient surface becomes perceptible again, a temporary calm repeatedly undone, yet never entirely erased. Air did not begin as something to breathe, it began as something released. As the surface shifted between molten expanses and fragile crust, pressure built beneath it. Deep within the mantle, volatile compounds dissolved in liquid rock rose slowly through fractures and conduits, carried upward by heat and buoyancy. When they reached lower pressures near the surface, they escaped, not in gentle breezes, but in vast plumes of gas. Volcanoes were not isolated mountains rising above a landscape. They were openings in a planet still learning how to separate its inside from its out. Outgassing became the primary architect of the early atmosphere. Carbon dioxide emerged in immense quantities, accompanied by water vapor drawn from minerals that had locked it away during formation. Methane and ammonia joined the mixture, each molecule contributing to a thick envelope that wrapped the planet tightly. Nitrogen accumulated as well, gradually becoming a stable background component. Oxygen, however, was absent as a free gas. Though bound within silicate rocks and water molecules, it did not circulate independently. The sky contained no trace of the breathable element that would one day define it. Under this growing atmosphere, sunlight filtered through a dense composition unlike anything familiar today. The young sun shone more faintly than it would in later eras, yet the abundance of greenhouse gases trapped thermal radiation with remarkable efficiency. Carbon dioxide absorbed outgoing infrared energy, redirecting it back toward the surface. Water vapor amplified this effect, creating a feedback loop in which warmth supported further evaporation and evaporation sustained warmth. Methane, though present in smaller amounts, added additional heat retention, particularly in an atmosphere lacking oxygen, to break it down quickly. The greenhouse effect in this context was not a subtle modulation but a dominant force. Without it, the dimmer sun might have left vast regions frozen. Instead, temperatures remained elevated, supporting liquid water whenever cooling permitted its condensation. The balance between radiative cooling and atmospheric insulation shaped the climate's earliest rhythms. Heat from below met heat held above, forming a layered structure in which surface conditions fluctuated yet avoided permanent descent into deep freeze. Above the surface, chemical reactions unfolded under ultraviolet light that penetrated the sky without obstruction from an ozone layer. Photochemical processes altered methane and ammonia, producing complex hydrocarbons that may have formed an organic haze. Such haze, similar in some respects to the atmosphere of modern Titan, could have scattered and absorbed sunlight, casting a diffuse glow across the planet. Instead of a clear blue dome, the sky may have appeared orange or reddish, tinted by suspended particles that refracted light toward warmer hues. This coloration was not merely aesthetic, but indicative of composition. In a thick carbon dioxide atmosphere, with suspended aerosols, shorter wavelengths of light scattered differently than in today's nitrogen and oxygen dominated air. The absence of Rayleigh's scattering in its familiar form meant blue would not dominate the sky. Instead, sunlight passing through dense gases and haze layers would soften into amber tones, especially during periods of intense volcanic activity when particulate matter increased. Over time, the atmosphere and surface entered into continuous exchange. Gases released from volcanic systems interacted with newly formed crust and with transient bodies of water. Carbon dioxide dissolved into early oceans when they existed, participating in chemical weathering that would eventually draw some of it down into carbonate minerals. Methane concentrations fluctuated as ultraviolet radiation broke molecules apart, only for further outgassing to replenish them. The sky was not static but responsive, shaped by cycles of release, reaction, and gradual transformation. In this early chapter, the atmosphere was both shield and furnace. It retained heat while also exposing the surface to high levels of radiation. It dimmed the sun's light through haze, while amplifying its warmth through greenhouse chemistry. What drifted above the planet was not a passive envelope, but an active participant in shaping conditions below, a dynamic mixture born from volcanic breath and bound closely to the restless ground beneath it. High above the turbulent surface and thickened skies, the young sun shone with a quieter intensity than it does today. Stellar models, built from nuclear physics and observations of similar stars, indicate that, around 4 billion years ago, the sun's luminosity was roughly 30% lower than its present output. Its core, still settling into long-term hydrogen fusion equilibrium, generated less radiant energy. Light traveled outward across space, just as it does now, but the total energy arriving at Earth's orbit was significantly reduced. Under modern atmospheric conditions, such a diminished sun would leave the planet locked in ice. Basic energy balance calculations suggest that with 30% less incoming solar radiation, Earth's surface temperature should have remained below the freezing point of water across much of the globe. Oceans, if present, would have solidified. Precipitation would have fallen as snow rather than rain. Reflective ice would have amplified cooling through increased albedo, returning more sunlight back to space. In a simple system governed only by solar input and reflection, early Earth should have been a frozen sphere orbiting a pale star. Yet, geological evidence implies the presence of liquid water during this period. Ancient zircon isotopes hint at interaction with hydrospheres. Sedimentary structures in younger Archean rocks suggest that persistent oceans existed not long after the Hadean gave way. This apparent contradiction between a faint sun and a wet planet is known as the faint young sun paradox, a tension between astrophysical expectation and geological record. Resolving it requires looking not upward alone but inward, toward the chemistry of the atmosphere described before. Greenhouse gases formed a thermal blanket far thicker than the one enveloping Earth today. Carbon dioxide concentrations were likely many times higher than modern levels, sustained by volcanic outgassing and limited removal through weathering during the planet's early stages. Water vapor, itself a potent greenhouse gas, would have accumulated wherever surface temperatures permitted evaporation. Methane, produced through abiotic reactions in a reducing atmosphere and perhaps early biological processes later on, absorbed infrared radiation in spectral regions complementary to carbon dioxide. Together, these gases altered the planet's radiative balance, trapping outgoing heat and elevating surface temperatures beyond what solar input alone would dictate. Climate modeling suggests that sufficiently high carbon dioxide levels could compensate for a 30% fainter sun, maintaining global mean temperatures above freezing. The atmosphere did not simply add warmth in a linear fashion. Feedback loops amplified its effects. Warmer conditions increased water vapor, which strengthened greenhouse trapping, which further elevated temperature. At the same time, cloud formation introduced complexity. Clouds reflect incoming sunlight while also trapping outgoing infrared radiation, and the balance between these opposing effects depended on cloud altitude, thickness, and particle composition. This early climate likely oscillated between extremes. Periods of enhanced volcanic activity could inject additional greenhouse gases, driving warming phases. Conversely, chemical weathering of emerging crust could gradually draw down carbon dioxide, reducing the greenhouse effect and allowing cooling to proceed. Without an ozone layer, ultraviolet radiation influenced atmospheric chemistry, altering methane lifetimes and haze formation, which in turn affected planetary albedo. The system was dynamic, sensitive to shifts in both internal and external forcing. Rather than a stable equilibrium, early Earth may have existed near the boundary between freezing and overheating, sustained by a delicate interplay of solar output, atmospheric composition, and geological processes. The faint young sun did not condemn the planet to permanent ice, nor did greenhouse warming render it uniformly torrid. Between these forces, climate fluctuated, sometimes edging toward cold, sometimes toward warmth, yet remaining within a range that allowed liquid water to persist across significant spans of time. In that subtle balance, the foundations of long-term habitability began to take hold. Moisture first lingered not as rain, nor as sea, but as vapor suspended within a dense and heated sky. As the surface cooled from its earlier extremes and solid patches endured for longer intervals, water vapor accumulated above them in thickening layers. The source of that vapor lay partly within the planet itself. Minerals forged deep in the mantle carried hydrogen and oxygen bound within their crystalline structures. When magma ascended and pressure dropped, these components escaped as steam, rising through fissures and vents in vast volumes. Volcanic exhalations released water continuously, building an atmosphere heavy with humidity. At the same time, external contributions continued to arrive. Primitive asteroids rich in hydrated minerals crossed Earth's path, and cometary bodies containing ice swept inward from colder regions of the solar system. Not every impact preserved its cargo. High-energy collisions could disperse volatile compounds back into space. Yet a fraction of this incoming water survived, integrating into the growing atmospheric reservoir or settling directly upon the surface. Isotopic comparisons between terrestrial water and certain carbonaceous chondrites suggest that these rocky bodies played a significant role in supplementing what the mantle provided. As temperatures gradually declined during quieter intervals, the saturated atmosphere approached condensation thresholds. Clouds formed, thick and expansive, composed of droplets suspended above a landscape still adjusting to structural stability. When cooling proceeded far enough, rain began to fall, not as isolated storms but as prolonged episodes of precipitation. Some models propose that once condensation started in earnest, rainfall may have persisted for thousands of years, feeding depressions and pooling within newly formed basins. The first oceans did not appear in a single moment, but gathered gradually, accumulating from continuous downpour and runoff. Evidence for early oceans comes from the same ancient zircons that hinted at prior crustal cooling. Oxygen isotope ratios within these crystals imply interaction with liquid water at temperatures consistent with surface conditions, rather than deep mantle environments. Some zircons, dated to approximately 4.3 billion years ago, suggest that water was present surprisingly soon after the most violent phases of planetary assembly. These clues do not reveal vast, tranquil seas identical to modern oceans, yet they indicate that stable bodies of liquid water may have existed intermittently, even during the Hadean. The presence of water did not guarantee permanence. Large impacts remained part of Earth's environment, and each sufficiently energetic collision had the potential to vaporize significant portions of surface water. When oceans were shallow or regional, a single major impact could convert liquid to steam in an instant, injecting enormous quantities of vapor back into the atmosphere. This vapor would later cool and condense once more, initiating another cycle of rainfall. The hydrologic system during this era was likely episodic, oscillating between phases of condensation and evaporation driven by external shocks and internal heat. Chemical interactions between water and rock began almost immediately. Newly formed crust reacted with circulating fluids, altering mineral compositions and drawing certain elements into solution. These interactions contributed to the early carbon cycle by dissolving atmospheric carbon dioxide into rainwater, which then formed carbonic acid capable of weathering silicate rocks. Such processes gradually linked the atmosphere, hydrosphere, and lithosphere into a dynamic network of exchange. Through these cycles of release, delivery, condensation, and loss, water established a persistent presence. Oceans may have retreated and returned many times, yet with each return, they reshaped the surface more deeply. What began as vapor exhaled from molten interiors evolved into lakes and seas that carved, dissolved, and transformed the planet's exterior. Even amid instability, liquid water endured long enough to leave a geochemical trace, marking the quiet emergence of one of Earth's most defining features. The moon keeps a record that Earth no longer can. Its surface, lacking atmosphere, water, and active tectonics, preserves scars that on Earth would have been erased. Across its highlands stretch overlapping craters, basins within basins, each rim casting long shadows over an otherwise silent plain. Radiometric dating of lunar samples, brought back during the 20th century, revealed that several of the largest impact basins formed around 3.9 billion years ago. This clustering of ages led to the proposal of a distinct episode known as the Late Heavy Bombardment, a period when impact rates may have intensified dramatically across the inner solar system. According to this hypothesis, the relatively declining barrage that followed planetary formation was interrupted by a spike in collisions. Massive objects, some dozens to hundreds of kilometers across, would have struck not only the Moon, but also Earth, Mercury, and Mars. On the Moon, the Imbrium and Oriental basins stand as immense remnants of this era, their formation dates aligning within a comparatively narrow window of geological time. If such impacts were widespread, Earth would have experienced similar events, though its dynamic surface has obscured direct evidence. Not all researchers agree that a discrete spike occurred. An alternative interpretation suggests that the apparent clustering of lunar impact ages may reflect sampling bias. Apollo missions collected rocks primarily from regions influenced by the Imbrium basin, potentially skewing age distributions. Some models propose a more gradual decline in impact frequency, without a sharp surge at 3.9 billion years ago. Others incorporate dynamical simulations of planetary migration, particularly movements of the giant planets, which could have destabilized reservoirs of small bodies and redirected them inward in waves rather than a singular pulse. Regardless of whether impacts peaked abruptly or tapered more smoothly, the late Hadean and early Archean were marked by continued collisions of considerable magnitude. When large impactors struck Earth, the energy released equaled or exceeded millions of times the most powerful modern nuclear detonations. Kinetic energy transformed instantly into heat, pressure, and shock. Rock at the point of contact vaporized. Surrounding material melted and flowed outward in sheets. Impact basins hundreds of kilometers across may have formed, their rims towering briefly before gravitational collapse softened them. Such events reshaped the crust repeatedly. Newly formed surface layers fractured and were buried beneath ejecta blankets composed of fragmented debris. In some cases, impacts may have penetrated through thinner crust into underlying mantle, bringing deeper material upward and mixing it with surface rock. Hydrothermal systems likely formed in the aftermath of these collisions as residual heat circulated through fractured crust, altering minerals and creating chemical gradients. Each impact was both destructive and generative, erasing prior structures while introducing new materials and thermal energy. On a planet that already recycled its outer layers, repeated impacts accelerated turnover. Crust that had begun to thicken could be shattered and partially melted, resetting geological clocks and redistributing elements. The cumulative effect of numerous large collisions contributed to a patchwork surface in constant transformation. Some models estimate that ocean vaporization could have occurred during the largest events, though recovery through condensation would have followed as the atmosphere cooled. The debate over the late heavy bombardment continues because Earth's earliest history is inferred through indirect records, comparative planetology, and numerical simulation. The Moon offers a preserved archive, yet interpretation depends on limited samples and complex crater counting techniques. Whether impacts surged sharply or waned gradually, their influence during this interval was profound. Through cycles of crater formation, crustal melting, and thermal pulses, repeated collisions shaped the evolving planet, imprinting patterns that guided its transition into a more stable and enduring world. Water gathered patiently, yet it remained vulnerable to forces still moving through space. When a sufficiently large impactor struck a world already holding shallow seas, the effect extended far beyond the crater itself. Numerical simulations that combine impact physics with atmospheric dynamics show that collisions involving objects tens of kilometers wide could deliver energy equivalent to the heat required to vaporize significant fractions of surface. Oceans. In extreme scenarios, especially during periods of heightened bombardment, entire global oceans may have been converted to steam in a matter of days. The mechanism is direct and relentless. Kinetic energy transforms into thermal energy upon impact, raising temperatures locally to thousands of degrees and driving shock waves outward through crust and water alike. Steam expands rapidly, injecting vast amounts of water vapor into the atmosphere. If the ocean is not too deep and the impact sufficiently energetic, the vaporization can become nearly global as superheated ejecta re-enters the atmosphere and radiates heat downward. The process is not a gentle evaporation but a phase transition forced by shock and heat, stripping liquid water from the surface and lifting it skyward. In the aftermath, Earth would have been wrapped in a thick steam atmosphere. Water vapor is an efficient greenhouse gas, and such an envelope would trap outgoing infrared radiation intensely. Surface temperatures could remain elevated for extended periods, even after the initial impact heat dissipated. The planet would resemble a pressure cooker on a planetary scale, with atmospheric densities far greater than today's and clouds forming at high altitudes within a deeply saturated sky. Cooling, however, proceeds inexorably as heat radiates into space. Climate models suggest that recondensation times depend on the depth of the original ocean and the magnitude of the impact. For moderate vaporization events, oceans might reform within thousands to tens of thousands of years. For the most extreme scenarios, full recovery could require longer spans, perhaps hundreds of thousands of years, as the atmosphere gradually lost heat and water droplets grew heavy enough to fall. Once condensation thresholds were crossed, rainfall would not occur as scattered storms, but as global, persistent downpours. Imagine a world where clouds cover the entire planet and rain falls continuously, each drop part of a hydrological reset. Precipitation rates during these intervals may have far exceeded modern tropical storms, with sheets of water descending across continents and basins alike. As the surface cooled sufficiently, steam condensed into liquid that pooled once more into oceans. Rivers may have carved temporary channels across newly fractured crust, transporting dissolved minerals back toward low-lying regions. The cycle of boiling and raining did not erase water permanently, but redistributed it, reshaping landscapes in the process. This cycling between ocean and vapor likely occurred multiple times during the Hadean. Each large impact acted as a thermal pulse, sending water upward. Each subsequent cooling allowed it to return. Over time, as bombardment declined and crust thickened, these extreme oscillations diminished in frequency. The persistence of water through repeated vaporization events suggests resilience within the system. Even when lifted entirely into the sky, water remained gravitationally bound, waiting for temperatures to fall. Such episodes influenced atmospheric chemistry as well. Steam-rich atmospheres altered reactions among carbon dioxide, nitrogen, and trace gases, potentially modifying greenhouse strength and surface conditions. Hydrothermal systems could have flourished after impacts, as residual heat circulated through fractured rock beneath reforming oceans. In this early world, the boundary between sea and sky was not fixed but fluid. Oceans could vanish into vapor and then descend again as rain, linking surface and atmosphere in a cycle driven by both celestial impact and planetary cooling. Through these repetitions, water endured, shaping the planet again and again, even when briefly lifted beyond the horizon. Solid ground, when it began to endure, did not arrive as sweeping land masses, but as scattered fragments rising quietly above a restless interior. In isolated regions where cooling had progressed further and melting events had become less frequent, thicker sections of crust accumulated. These were not continents in the modern sense, yet they possessed a quality that set them apart from surrounding terrain. They were lighter. As magma differentiated and crystallized, minerals rich in silica formed buoyant assemblages less dense than the underlying mantle. Through partial melting processes, especially in zones influenced by water, felsic compositions emerged. Granite-like materials began to appear, composed of quartz and feldspar that resisted sinking back into deeper layers. Their lower density allowed them to float upon the hotter, heavier mantle beneath, much as ice floats upon water. In a planet still young and thermally dynamic, this buoyancy offered a kind of survival advantage. These tiny protocontinents may have formed in patches, perhaps only tens to hundreds of kilometers across. They rose slowly, not as peaks piercing a skyline, but as persistent rafts within an evolving crust. Beneath them, mantle convection continued to circulate heat and material, yet the lighter crustal fragments were less easily recycled. Where denser basaltic crust might founder and descend, these silica-rich sections tended to remain at the surface. Over time, they thickened through additional melting and differentiation, gaining structural stability. The evidence for such early continental nuclei does not come from intact landscapes, but from minerals carried forward through deep time. Ancient zircons, again serving as durable witnesses, contain chemical signatures that suggest formation within evolved crust rather than primitive basalt. Some crystals record temperatures and pressures consistent with processes resembling modern subduction zones, where slabs of crust sink and trigger melting in the mantle above. This implies that tectonic-like movements, though not identical to present-day plate tectonics, may have already been underway. Geodynamic models support the idea that early Earth could have experienced vigorous vertical tectonics. The mantle was hotter, convection currents more intense, and crust thinner. Instead of large, rigid plates sliding across the globe, early tectonics may have involved frequent overturning and localized subduction of small crustal fragments. In such a regime, lighter felsic patches would have been preferentially preserved, while denser oceanic-style crust recycled more readily. Through repeated melting events, these buoyant fragments could gradually assemble into more substantial land masses. The interaction between water and rock likely played a significant role in this transformation. Water lowers the melting point of mantle materials and influences the viscosity of rocks, facilitating the generation of silica-rich melts. As oceans became more persistent and hydrothermal systems circulated fluids through crust, conditions favorable for continental crust formation increased. In this way, the hydrosphere and lithosphere acted in concert, shaping the architecture of the emerging planet. Over millions of years, these early continental seeds may have collided and merged, forming larger composite blocks. Their surfaces would have remained unstable compared to later continents, fractured by impacts and reshaped by volcanic activity. Yet their persistence marked a turning point. Instead of a surface dominated entirely by rapidly recycled basalt, areas of long-lived crust began to anchor geological processes. From scattered, buoyant fragments arose the foundations of future continents. They did not announce themselves with permanence at once, but through gradual accumulation and selective survival. Within their crystalline structures lay the first hints of enduring land, signaling that the planet's outer shell was beginning to differentiate not only internally but also across its surface, shaping a more varied and lasting terrain. Across the young planet, the ground did not remain still for long. Beneath the thickening crust, heat continued to build and migrate, seeking release through fractures and weak zones. The mantle, still far hotter than it would be in later ages, convected with greater intensity. Plumes of partially molten rock rose steadily, thinning the surface from below and opening pathways for magma to reach open air. Volcanoes were not isolated landmarks set against stable horizons. They were expressions of a planet in continuous exhalation. Eruptions occurred with a frequency difficult to imagine in the modern world. Vast fissures split the crust, allowing basaltic lava to pour outward in sheets that traveled for many kilometers before cooling. Instead of steep stratovolcanoes alone, immense flood basalts may have dominated certain regions, spreading across wide expanses and burying earlier terrain beneath fresh layers of dark, dense rock. Each flow thickened the crust locally, while also sealing away traces of what lay beneath. Over time, repeated eruptions created stacked sequences, building plateaus that rose and fractured under their own weight. These lavas were rich in iron and magnesium, characteristic of a mantle that melted more readily under the higher internal temperatures of the era. The viscosity of such magma allowed it to travel far before solidifying, smoothing landscapes into broad plains of basalt. As it cooled, gases trapped within the melt escaped, rising through vents and cracks in shimmering waves. Carbon dioxide, water vapor, sulfur compounds, and trace gases streamed upward, feeding directly into the atmosphere that continued to evolve overhead. Outgassing did more than thicken the air. It regulated climate over long timescales. Carbon dioxide, released from volcanic systems, contributed to greenhouse warming, while sulfur dioxide, interacting with sunlight, could form aerosols that reflected incoming radiation, temporarily moderating temperatures. The balance between these opposing effects likely fluctuated as volcanic intensity varied. Over millions of years, the steady addition of gases shaped atmospheric composition as profoundly as any impact event or ocean cycle. Beneath the surface, volcanic heat drove another important process. When seawater or groundwater percolated downward through fractures in newly solidified crust, it encountered hot rock and returned upward, enriched with dissolved minerals. Hydrothermal systems formed along spreading centers and around intrusive bodies of magma. These systems circulated fluids in continuous loops, transporting heat from the interior to the surface. Chimneys of mineral precipitate may have accumulated where hot fluids met cooler water, creating porous structures that concentrated chemical gradients. Such hydrothermal environments provided complex chemical landscapes. Dissolved metals, sulfur compounds, and reduced gases mixed in varying concentrations, creating conditions conducive to intricate reactions. Even before life emerged, these systems likely acted as chemical laboratories, accelerating interactions among dissolved elements. They also altered surrounding rock through metamorphism and mineral exchange, further modifying the crust's composition. Volcanic activity during this interval was not an isolated phenomenon, but a defining characteristic of the planet. The thin crust, still adjusting to internal dynamics, cracked and reformed repeatedly under thermal stress. Lava resurfaced wide regions, erasing older features while constructing new ones. Outgassing linked interior processes to atmospheric evolution, while hydrothermal circulation connected deep heat to ocean chemistry. In this world of persistent eruption, Stability was measured not by stillness, but by rhythm. Magma rose, spread, cooled, and fractured. Gases escaped and accumulated. Fluids circulated through rock and returned altered. Volcanoes functioned as the conduits through which the planet reorganized its energy, transferring heat from the depths to the surface, and, in doing so, shaping the evolving interface between solid ground, ocean, and sky. Deep beneath the shifting crust and circulating mantle, motion continued in darkness. The metallic core, formed early through differentiation, remained intensely hot, yet it did not exist in static stillness. Within that sphere of iron and nickel, temperature gradients drove slow, persistent convection. As Earth radiated heat into space over millions of years, the outer core remained liquid, while the innermost region began the earliest stages of crystallization. Solid iron nucleated at the very center, and as it formed, lighter elements were excluded and driven outward into the surrounding fluid. This gradual solidification altered the core's dynamics. The release of latent heat, combined with compositional buoyancy from expelled light elements, intensified convective circulation in the liquid outer core. Moving conductive material within a rotating planet gives rise to what physicists call a dynamo process. Electrical currents generated by this motion produced magnetic fields, and those fields, in turn, reinforced the currents in a self-sustaining cycle. Though the precise timing remains debated, paleomagnetic evidence from ancient minerals suggests that a functioning magnetic field may have existed by at least the early Archean, and perhaps even during the late Hadean. This magnetic field did not form as a static bar magnet, but as a dynamic, evolving structure extending outward into space. Lines of magnetic force emerged near the poles and looped back toward the surface, creating a magnetosphere that interacted directly with charged particles streaming from the sun. The young sun, more active and variable than today, emitted stronger solar winds and frequent eruptions of energetic particles. Without protection, such streams can strip atmospheric gases through a process known as sputtering, gradually eroding a planet's gaseous envelope. On Earth, the magnetosphere deflected much of this solar wind, guiding charged particles along magnetic field lines toward the poles rather than allowing them to bombard the atmosphere uniformly. Even in this early era, when the field may have been somewhat weaker or more variable, it likely provided a crucial buffer. By diverting high-energy particles, the magnetic shield reduced the rate at which lighter molecules escaped into space. Nitrogen and carbon dioxide, heavier than hydrogen, remained gravitationally bound more easily, but persistent exposure to intense solar wind could still enhance atmospheric loss over geological timescales. Comparative planetology offers perspective. Mars, smaller and cooling more rapidly, appears to have lost its global magnetic field relatively early in its history. Without sustained dynamo action, its atmosphere thinned, and much of its early water inventory disappeared. Venus, though similar in size to Earth, lacks a significant intrinsic magnetic field today, relying instead on a weaker induced magnetosphere generated by interactions between its atmosphere and the solar wind. Earth's internally generated field, by contrast, originates deep within its core and remains robust across billions of years. The early magnetic shield did not eliminate all atmospheric escape, nor did it create conditions of perfect stability. Solar activity still influenced the upper atmosphere, driving complex interactions and energizing chemical reactions. Yet the presence of a protective field altered the balance. It allowed Earth to retain substantial portions of its volatile inventory during a period when the Sun's behavior was more volatile than in later epochs. As the inner core continued its slow growth and convection persisted within the outer core, the dynamo strengthened and stabilized. The invisible field encircled the planet, linking deep interior processes to space environment conditions. In this way, events unfolding thousands of kilometers below the surface shaped the fate of air and water above. The magnetic shield became one more thread connecting Earth's internal evolution to its emerging habitability, quietly guarding the atmosphere even as surface and sky underwent their ongoing transformations. Color, in those early ages, did not belong to the sky as it does now. The familiar blue that arches over the modern world depends on a composition not yet present. Oxygen, which scatters shorter wavelengths of sunlight and allows azure tones to dominate daylight, had not accumulated in free form. It remained locked within silicate rocks and water molecules, bound chemically and unavailable to shape the atmosphere's optical character. Without molecular oxygen, there was no ozone layer high above to filter incoming ultraviolet radiation. The upper atmosphere was thinner in its defenses, more permeable to energetic light arriving from the young sun. Ultraviolet radiation streamed downward with greater intensity than it does today. Photons in this high energy range interacted directly with atmospheric gases, splitting molecules apart and driving chemical reactions that were both destructive and transformative. Methane, present in appreciable amounts in a reducing atmosphere, responded to this radiation by breaking into reactive fragments. These fragments recombined into complex hydrocarbons, some forming tiny suspended particles known as aerosols. Over time, such particles could accumulate into a substantial haze layer. This haze altered not only the chemistry but also the visual texture of the sky. Instead of the crisp scattering pattern produced by nitrogen and oxygen in the modern era, sunlight passed through an atmosphere thick with carbon dioxide, nitrogen, water vapor, and hydrocarbon particulates. Shorter wavelengths were scattered and absorbed differently, and the overall result may have been a muted, amber glow rather than a clear blue expanse. Observations of Saturn's moon Titan offer a distant analog. There, methane-derived photochemistry creates an orange haze that blankets the surface, diffusing sunlight into a persistent twilight tone. Early Earth's haze would not have been identical, yet the physical processes share certain similarities. The absence of ozone carried further implications. Ozone forms when ultraviolet radiation splits oxygen molecules, and the resulting atoms recombine in triatomic form. Without abundant oxygen, this protective layer could not arise. As a result, ultraviolet light penetrated deeper into the atmosphere and reached the surface with greater strength. This radiation influenced surface chemistry, particularly in shallow waters and on exposed mineral surfaces. It also contributed to the breakdown of greenhouse gases like methane, establishing a dynamic balance between production and destruction. Clouds, too, would have appeared different beneath this altered sky. Condensed water droplets and ice crystals reflect and scatter light in ways that depend upon background composition and particulate content. In an atmosphere laced with aerosols, clouds might have seemed tinged with warm hues, their edges glowing softly under filtered sunlight. Sunrises and sunsets, when light travels through a longer atmospheric path, could have been especially vivid, dominated by reds and oranges as shorter wavelengths were removed by scattering and absorption. The sky was not permanently uniform. Volcanic activity injected sulfur dioxide and ash temporarily increasing aerosol concentration and altering coloration further. Impact events lofted dust into the upper atmosphere, thickening haze and dimming sunlight until particles gradually settled. Between these episodic disturbances, photochemical processes sustained a background haze that gave the heavens a characteristic tint. Over time, as biological processes eventually began to release oxygen into the atmosphere, this visual identity would shift dramatically. But in the Hadean and earliest Archean, the sky bore little resemblance to what later generations would know. It was a canopy shaped by carbon compounds and ultraviolet light, lacking the deep blue that now defines a clear day. Under that amber dome, light filtered gently across ocean and stone, reflecting an atmosphere still in chemical infancy, yet already intimately linked to the evolving surface below. Time itself moved differently across the early planet. A single sunrise and sunset unfolded far more quickly than they do now, for Earth once spun with greater urgency. During its infancy, angular momentum from formation and colossal impacts left the planet rotating at a remarkable pace. Estimates based on tidal modeling and orbital mechanics suggest that early days may have lasted only 6 to 10 hours, compressing light and darkness into swift alternations that reshaped atmospheric and oceanic rhythms. A faster rotation alters more than the clock. The Coriolis force, which arises from planetary spin, becomes stronger as rotation accelerates. Air currents are deflected more sharply, winds organized into tighter bands, and weather systems confined to smaller scales. In a world where the atmosphere already differed profoundly in composition, this added rotational energy would have influenced cloud formation, storm intensity, and heat distribution between equator and poles. The rapid progression from day to night limited prolonged heating of any single region, potentially moderating surface temperature extremes despite high greenhouse concentrations. Beneath the sky, the oceans responded to this accelerated spin in equally significant ways. Faster rotation increases the strength of oceanic gyres and enhances mixing in surface layers. Water masses circulate with greater vigor when driven by brisk atmospheric patterns and shorter diurnal cycles. In the early Earth, when basins were still forming and coastlines unstable, such dynamic circulation could have distributed heat and dissolved chemicals efficiently across wide areas. Mixing also influenced the vertical transport of nutrients and minerals, linking shallow waters to deeper regions through turbulent exchange. Hovering above these oceans was a moon that orbited far closer than it does today. Shortly after its formation, the moon may have been only a fraction of its present distance, appearing immense in the sky. Gravitational interaction between the two bodies was correspondingly stronger. The tidal forces exerted on Earth were therefore significantly amplified, raising bulges in the oceans that were higher and more forceful. Twice during each shortened day, water would have surged inland and retreated, sculpting coastlines and stirring sediments across newly formed continental fragments. These amplified tides did more than reshape shorelines. They also acted as a brake on Earth's rotation. As tidal bulges were pulled slightly ahead of the moon due to the planet's rapid spin, gravitational interaction transferred angular momentum from Earth to its satellite. Gradually, this exchange slowed Earth's rotation and propelled the moon outward into a higher orbit. The process remains ongoing today, though at a much reduced rate. In the Hadean and early Archean, however, tidal deceleration occurred more swiftly, slowly lengthening the day over millions of years. Strong tides enhanced mixing at the ocean's margins, especially in shallow basins where water covered and uncovered mineral-rich surfaces repeatedly. Such cyclic wetting and drying environments may have concentrated chemical compounds and fostered complex reactions. Even without invoking biological processes, tidal pools would have experienced rapid changes in temperature, salinity, and chemical composition as water surged in and out under lunar influence. Thus, the swift rotation of early Earth, coupled with the gravitational pull of a nearer moon, set the tempo of the planet's external environment. Light and darkness alternated rapidly. Tides rose and fell with impressive amplitude. Winds organized in compact, energetic patterns. Over time, these forces gradually eased as rotation slowed and the moon receded. Yet, during the planet's formative epochs, the passage of a day was brisk and dynamic, imprinting a distinctive rhythm upon atmosphere and ocean alike. In the early ages of the planet, night did not rise over a familiar companion suspended at a modest distance. It lifted beneath a moon that dominated the sky, immense and luminous, orbiting perhaps 10-15 times closer than it does today. Its disk would have appeared vast, filling the heavens with a presence that seemed almost near enough to touch. The gravitational bond between Earth and its satellite was tighter then, their interaction more immediate and forceful. At such proximity, tidal forces were dramatically amplified. Gravity diminishes with distance, and when the moon was far nearer, its pull on Earth's oceans was profound. Water responded in broad swells, rising into bulges that traveled across the globe as the planet rotated beneath them. These were not the modest tides of modern shorelines, but immense surges capable of advancing far inland across low-lying terrain. Twice during each abbreviated day, seawater would have swept over coastal regions, only to withdraw again hours later, exposing freshly wetted rock to air and sunlight. Where early continental fragments met the ocean, these tides reshaped boundaries continuously. Sediment carried by surging water settled and was remobilized repeatedly. Basins deepened, channels shifted, and shorelines migrated with each cycle. In shallow regions, tidal currents mixed water vigorously, redistributing heat and dissolved minerals across wide areas. The mechanical energy delivered by these tides linked celestial motion directly to geological change. The magnitude of early tides also influenced internal dynamics. As the tidal bulges formed, Earth's rapid rotation carried them slightly ahead of the line directly beneath the moon. This misalignment created a gravitational torque that acted as a brake. Energy was transferred from Earth's spin to the moon's orbit, gradually slowing the planet's rotation while propelling the moon outward. The process was incremental, yet relentless. Over millions of years, days lengthened from perhaps 6-10 hours toward the slower rhythm recognized today. This exchange of angular momentum produced subtle but persistent consequences. Slower rotation altered atmospheric circulation patterns, easing the intensity of the Coriolis effect and expanding the scale of weather systems. Oceans adjusted as well, responding to lengthened days and changing tidal frequencies. Meanwhile, the moon receded, its orbit expanding in a slow spiral away from Earth. Laser ranging measurements in the modern era confirm that this outward drift continues, though at a far more measured pace than during those early epochs. The presence of a closer moon may also have influenced axial stability. Gravitational interaction between Earth's equatorial bulge and the moon exerted a stabilizing effect on the planet's tilt. With the moon so near, this stabilizing force was especially strong, helping to moderate variations in obliquity even while rotation slowed. Seasonal patterns, though different from those of later eras, were governed within a relatively constrained range by this celestial partnership. Thus, the early moon was not merely a distant ornament in the night sky. It was an active participant in shaping surface conditions and planetary evolution. Its nearness amplified tides that carved coastlines and stirred oceans. Its gravity gradually moderated Earth's spin. Its steady pull contributed to long-term axial stability. Over time, distance grew between the two bodies, and the dramatic tidal regime softened. Yet in those formative millions of years, the moon's looming presence left an imprint on Earth's rhythm, binding ocean, rotation, and sky in a single, continuous exchange. Beneath the surface of those early seas, the water was not clear in the way modern oceans appear. It carried a dense mixture of dissolved minerals, leached from newly formed crust, and delivered through volcanic and hydrothermal activity. The chemistry of these waters reflected a planet still adjusting to its own heat. Rocks that had only recently cooled encountered circulating fluids that penetrated fractures and pores, dissolving elements and transporting them back into the ocean. The result was a marine environment saturated with ions, metals, and reactive compounds. Iron was among the most abundant dissolved elements. Under the reducing conditions that prevailed in the absence of free oxygen, iron remained in its soluble ferrous form, drifting invisibly through the water column. Instead of precipitating as rust-colored oxides as it does in oxygen-rich seas, it accumulated in high concentrations. The oceans may have appeared tinted green or brown under certain lighting, influenced by suspended particles and the optical properties of dissolved metals. These were iron-rich seas, chemically distinct from any ocean that exists today. Carbon dioxide from the atmosphere dissolved readily into surface waters, forming carbonic acid that interacted with silicate minerals. Methane, though less soluble, could still enter solution under high pressures, while nitrogen existed primarily as dissolved molecular gas. Hydrogen sulfide, released through hydrothermal processes, added another reactive component to the mixture. Temperature played a crucial role in shaping these reactions. With higher global heat flow and frequent volcanic input, ocean temperatures may have been significantly warmer than modern averages, particularly near active spreading regions and shallow basins influenced by geothermal flux. Warm water accelerates chemical reactions. Molecules collide more frequently and with greater energy, increasing the likelihood of transformation. In such an environment, dissolved metals interacted with sulfides, carbonates, and silicates in a continuous network of reactions. Mineral precipitates formed around hydrothermal vents, where superheated fluids met cooler seawater, creating steep chemical gradients over small spatial scales. These gradients established zones of contrasting pH, redox state, and ion concentration, fostering localized pockets of intense reactivity. Lightning from thickened storm systems and ultraviolet radiation penetrating surface layers also contributed to marine chemistry. Electrical discharges could drive reactions among dissolved gases at the water's surface, while ultraviolet light energized certain compounds in shallow environments. Though damaging to complex organic structures, such radiation could also promote the formation of simple molecules from smaller precursors. The boundary between water and air became a chemically active interface, linking atmospheric composition directly to oceanic processes. Sediments accumulating on the seafloor recorded these interactions. Layers rich in iron, silica, and other precipitated minerals settled gradually, sometimes forming banded structures that would later serve as evidence of shifting chemical conditions. The continual cycling of elements between crust, ocean, and atmosphere maintained a dynamic equilibrium, even if that equilibrium fluctuated over time. This chemical complexity did not imply order in the conventional sense. Rather, it represented a state of organized instability where energy flowed through reactions and compounds transformed in response. Dissolved gases entered and exited solution. Metals shifted between oxidation states, and mineral surfaces catalyzed further change. In such waters, chemistry unfolded with intensity, shaped by heat from below and radiation from above. The oceans were not passive reservoirs, but active reactors, carrying within them the ingredients and conditions that would later support biological processes. In this phase of Earth's history, the seas embodied chemical chaos, yet within that turbulence lay structured pathways of transformation linking rock, water, and air into a single evolving system, far below the shifting surface, where sunlight never reached and pressure mounted with depth. Seawater found its way downward through fractured crust and encountered heat rising from within. As it descended, this water was transformed. It warmed, expanded, and reacted with surrounding rock, dissolving metals and altering minerals in a slow exchange. Eventually, buoyancy drove it upward again, emerging through openings in the seafloor as towering plumes of mineral-rich fluid. These hydrothermal vents were among the most dynamic environments on the early planet. Some vents expelled dark, particle-laden jets, known today as black smokers. The darkness comes from fine grains of iron sulfide and other minerals that precipitate instantly when superheated vent fluids meet colder seawater. In the Hadean and earliest Archean oceans, where iron was abundant and sulfur circulated freely, such chimneys may have been widespread. The plumes rose like underwater smoke, spreading and cooling as dissolved metals solidified into tiny crystals that drifted downward to the seabed. Around each vent, sharp chemical gradients formed, hot, alkaline fluids rich in hydrogen and reduced metals mixed abruptly with cooler, more oxidized seawater. Differences in temperature, pH, and redox potential created zones of contrast across distances of mere centimeters. In chemistry, gradients represent stored energy, and these boundaries provided natural interfaces where reactions could proceed efficiently. Molecules carried upward from the mantle encountered compounds dissolved in the ocean, and their interactions were shaped by steep contrasts in concentration and temperature. Unlike surface environments driven by sunlight, hydrothermal systems derived their energy directly from geothermal heat and chemical disequilibrium. Serpentinization reactions, in which seawater interacted with ultramafic rock, generated hydrogen gas, a potent reducing agent. When hydrogen encountered carbon dioxide dissolved in surrounding water, simple organic molecules could form under the right conditions. Mineral surfaces within vent chimneys offered catalytic sites, concentrating reactants and facilitating bond formation. Iron-sulfur minerals, in particular, possess structures capable of supporting electron transfer, an essential component of metabolic chemistry in later organisms. The architecture of vent systems further encouraged organization. Porous walls within chimneys contained microscopic cavities that acted as natural compartments. Within these confined spaces, molecules could accumulate and interact more readily than in the open ocean. Temperature gradients between the interior of a vent and surrounding seawater established convection currents on a small scale, circulating fluids through mineral-lined pores and continuously supplying fresh reactants. In such settings, chemistry unfolded with direction and continuity rather than random diffusion alone. Modern hydrothermal vent ecosystems provide insight into what these environments offer. Today, entire communities of microorganisms and multicellular life thrive around black smokers, deriving energy not from sunlight, but from chemical reactions involving hydrogen, sulfide, and other reduced compounds. Though such life forms evolved long after the Hadean, their existence demonstrates that geothermal systems can sustain complex networks based on chemical energy. They also reveal how mineral surfaces and steep gradients can support metabolic pathways in the absence of photosynthesis. In the early ocean, long before oxygen accumulated in the atmosphere, hydrothermal vents likely served as persistent hubs of chemical transformation. Heat from Earth's interior met the mineral-rich waters described earlier, and at these junctions, matter and energy flowed in concentrated patterns. Black smokers rose and collapsed, chimneys grew and fractured, fluids surged and cooled. Within this constant motion, gradients provided structure, minerals offered scaffolding, and energy drove reactions forward. These environments stand as plausible cradles of chemistry, places where the boundary between geology and biology began to blur in subtle, molecular ways. Long before cells or membranes shaped the boundaries of life, carbon was already assembling into intricate forms. Within the reactive oceans and atmospheres described earlier, simple molecules collided, broke apart, and recombined in patterns guided by temperature, pressure, and energy flow. Carbon dioxide drifted through air and dissolved in water. Methane responded to ultraviolet light. Nitrogen participated in reactions driven by lightning and geothermal heat. None of these processes required biology. They unfolded through abiotic chemistry, the spontaneous organization of matter under suitable conditions. Carbon possesses a unique versatility. Its ability to form four stable covalent bonds allows it to construct chains, rings, and branching networks far more varied than most other elements. In a reducing environment where methane and hydrogen were available, ultraviolet radiation could initiate reactions that built progressively more complex hydrocarbons. In aqueous settings, dissolved carbon dioxide and hydrogen generated by hydrothermal systems could combine through catalytic mineral surfaces, producing simple organic compounds such as formate, acetate, and other small molecules. Among the most significant of these were amino acids, the building blocks of proteins in modern organisms. Laboratory experiments have demonstrated that amino acids can form naturally when simple gases are exposed to energy sources. In the early 20th century, the Miller-Urey experiment simulated aspects of the primitive atmosphere by circulating methane, ammonia, hydrogen, and water vapor through an apparatus subjected to electrical discharges meant to mimic lightning. After days of operation, the system produced a suite of organic molecules, including several amino acids. Although our understanding of early atmospheric composition has evolved since that experiment, subsequent studies using alternative gas mixtures and energy sources have also yielded amino acids and related compounds. Hydrothermal environments offer another pathway. In vent systems, mineral catalysts, such as iron sulfides, can facilitate reactions between dissolved carbon and nitrogen compounds, encouraging the formation of organic molecules under high temperature and pressure conditions. The steep gradients and confined spaces within vent structures create microenvironments where molecules are concentrated and protected from dilution, increasing the likelihood of further chemical evolution. Organic compounds also arrived from beyond Earth. Meteorites, known as carbonaceous chondrites, contain a rich inventory of organic molecules, including amino acids, nucleobase analogues, and a variety of hydrocarbons. Analyses of meteorites such as the Murchison specimen, have revealed dozens of amino acids, some rarely found in terrestrial biology. Isotopic signatures within these molecules indicate formation in interstellar environments or within the parent bodies of asteroids, rather than contamination after landing. During periods of heavy bombardment, countless smaller fragments containing such organics would have rained down upon Earth's surface, supplementing the planet's internal chemistry with extraterrestrial material. Once present, these organic molecules interacted with mineral surfaces, dissolved in oceans, and circulated through hydrothermal systems. Concentration mechanisms, including evaporation in shallow pools or adsorption onto clay minerals, could enhance their stability and promote further reactions. Although individual molecules were fragile and easily altered, the continuous production and delivery from multiple sources ensured a persistent supply. In this chemical landscape, complexity increased gradually. Amino acids linked into short chains under certain conditions. Fatty acids assembled into membrane-like structures when immersed in water. Nucleotides may have formed through stepwise reactions involving simpler precursors. These processes were not directed toward life by intention, but emerged from the interplay of energy, matter, and environment. The first organic molecules marked a threshold in Earth's evolution, representing the transition from purely inorganic chemistry to a domain where carbon structures acquired the potential for replication, catalysis, and eventually, biology. In the oldest rocks that have survived the recycling of continents and the grinding of tectonic motion, there are faint chemical whispers that hint at something more than geology. These rocks do not preserve shells or bones, nor even clear cellular outlines. Instead, they carry signatures in carbon itself, subtle variations in isotopic ratios that suggest the possibility of biological processing at astonishing depths of time. Carbon occurs naturally in multiple isotopic forms, primarily carbon-12 and carbon-13. Living systems, as understood today, tend to preferentially incorporate the lighter isotope during metabolic reactions. This preference leaves behind a measurable difference: a skew in the ratio between carbon-12 and carbon-13 within organic remains compared to inorganic carbonates. In certain ancient rocks, dated to approximately 3.8 to 4.1 billion years, scientists have identified carbon isotopic ratios that resemble those produced by biological activity. These signals are embedded in metamorphosed sedimentary rocks from regions such as Greenland and Western Australia, places where fragments of Earth's earliest crust endured. Interpreting these signatures is not straightforward. Rocks from this era have experienced immense pressure and temperature during billions of years of tectonic reshaping. Metamorphism can alter mineral structures and potentially modify isotopic compositions. Some researchers argue that abiotic processes under high-temperature conditions can also fractionate carbon isotopes in ways that mimic biological patterns. Chemical reactions associated with hydrothermal systems, for instance, may generate reduced carbon with similar isotopic signatures. The debate therefore rests not only on measurement, but on context, the geological setting in which these signatures occur. In addition to isotopic evidence, there are controversial reports of microscopic structures within certain ancient rocks that resemble fossilized microbial filaments. Some formations, dated to around 3.8 billion years, exhibit layered sedimentary patterns that could have formed in shallow marine environments. Later, by approximately 3.5 billion years ago, stromatolites become more clearly established in the geological record, produced by microbial mats trapping and binding sediment. The question is whether such biological activity extended further back into the Hadean or very early Archean. Thermal models of early Earth, once thought to preclude stable habitats, now allow for intervals of relative calm between major impacts. Hydrothermal environments, subsurface niches, and even shallow oceans shielded from intense radiation could have provided refuges for primitive life forms if they arose. Laboratory experiments show that simple self-replicating molecules can form under certain conditions, and evolutionary theory suggests that once replication begins, natural selection rapidly favors stability and efficiency. If microbial life emerged as early as 4.1 billion years ago, it would imply that the transition from chemistry to biology occurred with surprising speed after the planet cooled sufficiently to sustain liquid water. Such rapid emergence would suggest that, given appropriate conditions, life may not be an exceedingly rare phenomenon, yet caution remains central to this interpretation. Extraordinary claims demand rigorous evidence, and the fragmentary record of deep time leaves room for alternative explanations rooted purely in geochemistry. What remains clear is that by 3.5 billion years ago, life was firmly established. The isotopic hints and possible microstructures, extending closer to 4 billion years, push the boundary of habitability nearer to the planet's formative upheavals. Within rocks shaped by heat and pressure lie chemical traces that may record the earliest chapter of biology. Whether those traces mark the definitive origin of life or represent prebiotic experimentation, they reveal that Earth's surface became hospitable to complex chemistry remarkably early in its history. Narrowing the interval between planetary chaos and biological persistence. Destruction on a planetary scale does not always imply total erasure. Even during epochs marked by repeated collisions and thermal upheaval, refuges can persist in places shielded from the most violent extremes. As large impactors struck the surface, converting rock to vapor and lifting oceans into steam, the effects were most severe at and above the crust. Beneath that surface layer, however, conditions changed more gradually. Rock is an effective insulator. Heat from an impact pulse dissipates with depth, and models of even the largest collisions suggest that while surface temperatures could soar high enough to sterilize exposed environments, subsurface regions a few kilometers below might remain comparatively temperate. Microbial life, if already present in the oceans or crust, could have retreated or persisted within pore spaces in rock, in fracture networks filled with water, or within sediment layers protected from direct heating. These underground niches would have buffered rapid temperature spikes and shielded inhabitants from intense ultraviolet radiation. Hydrothermal systems provided additional sanctuaries. The circulation of water through deep crust maintained habitats warmed by geothermal energy rather than solar input. If life emerged in such environments, it would have been adapted to darkness, chemical gradients, and fluctuating thermal conditions. Organisms living there would have encountered shifts in temperature and chemistry regularly, selecting for resilience and metabolic flexibility. When surface conditions deteriorated following an impact, these communities could endure below, sustained by chemical energy rather than sunlight. Ocean depth offered further protection. While shallow waters might heat dramatically, or even boil during massive impacts, deeper layers would be insulated by the thermal inertia of overlying water. Simulations indicate that complete sterilization of oceans to great depth would require impacts of extraordinary magnitude, rare even during the late heavy bombardment. In deep marine basins, pressures and temperatures change slowly compared to the surface, providing stability amid external chaos. If microbial ecosystems inhabited the deep ocean floor, particularly around vent systems, they might have survived cycles of impact-driven upheaval. Modern organisms demonstrate how robust life can be. Extremophiles discovered in deep subsurface mines, beneath kilometers of rock, thrive without sunlight, deriving energy from chemical reactions involving hydrogen and sulfur compounds. Thermophilic microbes flourish in boiling hot springs and hydrothermal vents, tolerating temperatures once thought incompatible with life. Some bacteria form endospores, dormant structures capable of withstanding desiccation, radiation, and extreme heat for extended periods. These examples do not prove ancient survival, yet they reveal that biology possesses mechanisms for enduring conditions similar to those likely encountered during early bombardment phases. Even if surface environments experienced episodic sterilization, recolonization from protected refuges could occur once conditions stabilized. Microbes surviving underground or in deep water would expand into newly formed habitats as temperatures cooled and oceans recondensed. The rapid reproduction rates characteristic of microbial life would allow populations to rebound quickly relative to geological timescales. In this light, impacts become less an absolute boundary and more a filter. They reshape landscapes and reset surface ecosystems, yet do not necessarily extinguish all living systems. The interplay between destruction and persistence reflects a planet whose interior and oceans offered layered protection. Within fractures of rock and depths of water, life, if present, could endure through cycles of catastrophe. Survival did not depend upon immunity to violence, but upon occupying niches where energy remained available and extremes were moderated. Such resilience, echoed in modern extremophiles, suggests that even in an age of frequent impacts, the continuity of life may have been preserved in hidden and enduring sanctuaries. Not all rocky planets share the same fate, even when born from similar materials within the same protoplanetary disk. In size and bulk composition, Earth and Venus are often described as twins. Their radii differ only slightly, and their masses fall within a narrow range. Both likely experienced early volcanic outgassing, magma oceans, and bombardment from remnant debris. Yet, over billions of years, their paths diverged dramatically. One came to host persistent oceans and a temperate climate. The other evolved into a world cloaked in thick carbon dioxide clouds, its surface hot enough to melt lead. Distance from the Sun played an essential role in this divergence. Venus orbits closer, receiving significantly more solar energy. Even during the era when the Sun's output was roughly 30% dimmer than today, Venus would have absorbed more radiation than Earth. Increased insolation influences atmospheric chemistry and surface temperature directly. On a planet slightly nearer the Sun, water vapor is more readily sustained in the atmosphere rather than condensed into long-lived oceans. Because water vapor is itself a powerful greenhouse gas, higher concentrations intensify warming in a reinforcing cycle. If surface temperatures rise enough to prevent condensation of water into stable oceans, a runaway greenhouse effect can unfold. In such a scenario, carbon dioxide, released through volcanic activity, accumulates without an efficient mechanism for long-term removal. On Earth, liquid water enables a critical stabilizing process known as the carbonate-silicate cycle. Carbon dioxide dissolves in rainwater, forming weak carbonic acid that reacts with silicate rocks. Weathering products are transported to the oceans, where carbon is locked into carbonate minerals and eventually subducted into the mantle. This cycle operates as a planetary thermostat, gradually reducing atmospheric carbon dioxide when temperatures climb. Venus, lacking stable surface water, could not establish this feedback loop. Without rain and ocean chemistry to sequester carbon, volcanic outgassing allowed carbon dioxide to build to extreme concentrations. The resulting dense atmosphere trapped enormous amounts of heat. Surface temperatures soared, preventing any late arriving water from remaining liquid for long. Ultraviolet radiation high in the atmosphere dissociated water molecules, and lighter hydrogen escaped into space, leaving oxygen to react with surface materials. Over time, the planet lost most of its water inventory. Earth's slightly greater distance from the Sun positioned it within a narrower band of thermal balance. Even under a fainter young sun, greenhouse gases maintained warmth without tipping irreversibly into runaway heating. When surface temperatures permitted water to condense, oceans formed and persisted for extended periods. Once oceans were established, they moderated climate through heat capacity and initiated the carbon cycling processes that limited atmospheric carbon dioxide accumulation. Plate tectonics, emerging gradually as the planet cooled, further enhanced this regulation by recycling carbonates and driving long-term exchange between crust and mantle. Magnetic shielding may also have contributed to atmospheric retention, reducing the rate at which lighter molecules escaped under solar-wind interaction. While Venus lacks a strong intrinsic magnetic field today, Earth's internal dynamo offered additional protection to its atmosphere and hydrosphere. Each of these factors, distance from the sun, presence of liquid water, carbon cycling feedbacks, and magnetic shielding, interacted over geological time to stabilize Earth's climate within habitable bounds. The contrast between the two planets underscores how small initial differences can amplify through feedback mechanisms. A modest shift in orbital position altered energy balance. That change influenced water retention, water-enabled carbon regulation, and carbon regulation shaped atmospheric composition. Through this sequence, Earth avoided the extreme greenhouse state that defines Venus. Instead, it maintained conditions in which oceans endured, continents evolved, and life ultimately took hold, guided by a chain of interdependent processes rooted in planetary physics and chemistry. Size, though subtle in difference, can alter destiny across billions of years. Mars formed from similar raw materials within the same young solar system, yet its smaller mass set in motion a distinct trajectory. With less gravitational pull, it gathered a thinner atmosphere and retained a reduced inventory of internal heat. These initial variations shaped its long-term evolution in ways that stand in contrast to Earth's path. Internal heat serves as the engine of planetary activity. On Earth, residual heat from formation, sustained radioactive decay, and gradual core crystallization have driven mantle convection and maintained a liquid outer core. This motion powers a magnetic dynamo that continues to generate a global magnetic field. Mars, by comparison, cooled more rapidly. Its smaller volume relative to surface area allowed heat to escape efficiently, diminishing convective vigor in its interior. Geological evidence suggests that Mars once possessed a magnetic field early in its history, recorded as remnant magnetization in ancient crustal rocks. Over time, however, its dynamo ceased, and the global field faded. The disappearance of a magnetic shield altered Mars's interaction with the solar wind. Charged particles streaming outward from the Sun encountered little resistance once the intrinsic field weakened. Over extended periods, these interactions gradually stripped away atmospheric particles, particularly lighter components. Instruments aboard orbiting spacecraft have measured ongoing atmospheric escape from Mars, confirming that even today, the solar wind continues to erode its thin envelope. As atmospheric density declined, surface pressure fell. Lower pressure reduces the boiling point of water, limiting its stability as a liquid. Mars displays geomorphological features such as valley networks and sedimentary layers that indicate liquid water once flowed across its surface. Yet, as the atmosphere thinned and temperatures decreased, these watery intervals diminished. Water either froze into subsurface ice or was lost to space through photodissociation and escape of hydrogen. Earth's greater mass provided a more secure gravitational hold on its atmosphere and hydrosphere. Even without a magnetic field, gravity alone assists in retaining heavier gases, but the combination of strong gravity and sustained magnetism enhances atmospheric stability. Earth's larger interior also retained heat more effectively, prolonging mantle convection and core motion. This extended geological activity supported volcanic outgassing, plate tectonics, and carbon cycling, processes that regulate climate over long timescales. Tectonic recycling on Earth allows carbon dioxide and other volatiles to be exchanged between surface and interior. When greenhouse gases are drawn down through weathering and sedimentation, subduction returns them to the mantle, where they can be released again through volcanism. Such feedback maintains a dynamic equilibrium. Mars, lacking plate tectonics in the modern sense, experienced less efficient recycling. Its volcanic activity, concentrated in massive shield volcanoes like Olympus Mons, persisted for long intervals, but without the global plate interactions that continuously reshape Earth's crust. Distance from the Sun also plays a role, yet Mars resides within a region where liquid water could exist under favorable atmospheric conditions. The decisive differences lie in size, heat retention, and magnetic longevity. A smaller planet cools faster. A cooled core ceases its dynamo. Without a sustained magnetic field, atmospheric erosion proceeds more readily. With declining atmosphere, climate shifts toward cold and dryness. Through these interconnected processes, Earth and Mars diverged. One maintained internal energy sufficient to power a magnetic shield and tectonic renewal. The other gradually lost these capacities. The comparison underscores how planetary mass influences thermal evolution and atmospheric persistence. Earth did not become Mars because it retained the heat and dynamism required to shield its air and sustain its climate, preserving conditions that allowed water and life to endure across immense spans of time. There was no single sunrise that marked the end of the Hadean, no boundary line drawn across stone or sea. Instead, change unfolded slowly, almost imperceptibly at first, as the rhythms of violence began to soften and intervals of calm grew longer. The sky still carried haze, the mantle still stirred beneath the crust, yet the tempo of catastrophe eased. Over time, the population of large wandering bodies in the inner solar system declined. Many had already collided with planets or been ejected outward by gravitational interactions. The era of frequent massive impacts gradually waned. Collisions still occurred, but they were less likely to vaporize oceans or remelt entire regions of crust. With each passing million years, the probability of planet-wide sterilizing events diminished. The surface gained longer stretches of continuity between upheavals, allowing geological and chemical processes to mature. Oceans, once subject to cycles of evaporation and recondensation, began to persist more steadily. Liquid water remained pooled within basins for extended spans, rather than vanishing into steam after every major impact. The hydrological cycle stabilized into patterns of evaporation, cloud formation, and rainfall that no longer reset completely with each collision. Shorelines, though still mobile, endured long enough for sediment layers to accumulate and for chemical interactions between rock and water to deepen. The presence of continuous oceans moderated climate further, buffering temperature swings and distributing heat across latitudes. Beneath these waters, crust thickened incrementally. Partial melts differentiated into buoyant continental fragments, and tectonic processes evolved from vertical overturn to more organized horizontal motion. While plate tectonics in its modern form may not yet have been fully established, the outer shell of the planet became stronger and more structured. Repeated recycling still occurred, yet larger, more stable blocks of crust began to resist complete reabsorption into the mantle. Thickness increased, and with it came greater resilience against surface disruption. Internal heat remained substantial, sustaining volcanic activity and hydrothermal systems, but the overall energy of the planet was trending downward. Core convection continued to support a magnetic field, preserving atmospheric integrity. Carbon cycling between atmosphere, ocean, and crust operated with increasing efficiency as weathering processes extended across more permanent land masses. The interplay between internal and external forces settled into a dynamic equilibrium rather than constant reset. The transition from Hadean to Archean was therefore not abrupt but cumulative. It represented a threshold crossed gradually as stability began to outweigh chaos. With fewer colossal impacts, persistent oceans, and thickening crust, the planet entered a phase in which surface environments could evolve over longer, uninterrupted periods. Geological memory extended further back, preserved in rock sequences rather than erased repeatedly. This stabilization did not eliminate transformation. Volcanoes still erupted, continents still shifted, and climate still fluctuated. Yet, the scale of change became less universally catastrophic and more regionally varied. Conditions conducive to sustaining life, if already present in hidden niches, could now expand more reliably across surface and subsurface environments. The foundations laid in earlier turmoil were no longer constantly dismantled. By the close of the Hadean, Earth had not become tranquil in the human sense, but it had achieved continuity. Oceans endured, crust held, impacts, though present, no longer dominated the planetary narrative. Through gradual adjustment, rather than sudden revelation, the world moved beyond its most volatile infancy. The stage was set for deeper biological and geological complexity to unfold upon a surface that, at last, could remember its own past. Geologic time does not turn pages, it deepens them. As the Hadean yielded to the Archean, the planet did not reinvent itself, but settled into patterns capable of continuity. Rocks from this younger era become more abundant in the record, preserving textures and chemical traces that earlier eons could not retain. Within these surviving formations, the evidence of biology grows clearer and less ambiguous. By approximately 3.5 billion years ago, certain sedimentary structures appear in shallow marine deposits that bear hallmarks of life. Layered domes and rippled mounds, now known as stromatolites, rise from ancient carbonate platforms. These structures form when microbial mats trap and bind sediment while precipitating minerals from surrounding water. As thin layers accumulate over time, they create finely laminated buildups that resemble low-rounded reefs. The regularity and organization of these laminations differ from purely inorganic processes, pointing toward coordinated biological activity. Microorganisms responsible for stromatolite formation are thought to have included cyanobacteria and other photosynthetic microbes, though early communities may have been metabolically diverse. Their activity altered local chemistry, by mediating the precipitation of calcium carbonate and by interacting with dissolved ions in seawater. While the Archean atmosphere still lacked free oxygen in significant quantities, biological processes were already influencing Earth's surface environment at small scales. Isotopic signatures from Archean rocks reinforce this picture. Carbon fractionation patterns become more consistent with biological metabolism, and sulfur isotopes display mass-independent fractionation patterns that reflect atmospheric chemistry under low oxygen conditions. Together, these signals indicate that life was not only present, but metabolically active and widespread by the mid-Archean. Despite this biological presence, oxygen remained scarce in the atmosphere. Even if some microbes were performing oxygenic photosynthesis, the oxygen they produced did not accumulate freely. Instead, it reacted quickly with abundant reduced minerals, particularly dissolved iron in the oceans and iron-bearing rocks on land. The result was a vast chemical sink that consumed oxygen as rapidly as it was generated. Banded iron formations, layered deposits of iron-rich minerals alternating with silica, would later record episodes of oxygen interacting with seawater, iron, but for long intervals, the atmosphere itself remained largely anoxic. The sky above these early oceans therefore retained its muted tones, unshaped by an ozone layer or oxygen-rich scattering. Ultraviolet radiation still penetrated the upper atmosphere, and surface environments were governed by greenhouse gases and volcanic emissions rather than by modern atmospheric composition. Yet beneath this sky, microbial ecosystems flourished in marine shallows, deep hydrothermal systems, and subsurface niches. The transition into the Archean marks not the sudden appearance of life, but the first clear geological preservation of its presence. Structures, isotopes, and sedimentary patterns collectively testify that by this time the biosphere had established a durable foothold. The planet's crust was thick enough to retain records, oceans were stable enough to sustain evolving communities, impacts no longer erased surface history with regularity. Life in the Archean remained microscopic and simple in form, yet its influence was profound. Through metabolic reactions and mineral interactions, microbial communities began to reshape global chemistry. Over immense spans of time, their cumulative activity would transform the atmosphere itself. For now, however, the Earth stood in a quiet equilibrium, oceans persistent, crust enduring, oxygen still bound within rock and water. The stage was set for slow but consequential change, recorded layer by layer in stone that could finally remember. Cooling is not an event, but a long negotiation between interior and space. From its earliest molten beginnings, Earth radiated energy outward, shedding the excess heat of accretion, impacts, and radioactive decay. Yet this release unfolded across immense spans of time. As billions of years passed, the balance between internal generation of heat and external loss shifted gradually, altering the character of the planet from within. Heat escapes through conduction across the crust, through convection in the mantle, and through volcanic eruptions that deliver molten material to the surface. In its youth, vigorous mantle convection drove rapid overturn and extensive melting over time. As the interior temperature declined, convection patterns evolved. The mantle remained dynamic, but its movements became more structured. Rather than chaotic vertical cycling alone, horizontal components of motion strengthened. Lithospheric fragments began to move relative to one another, marking the early stages of plate tectonics. The emergence of plate tectonics represented a new mode of planetary cooling. Oceanic crust formed at spreading centers where mantle material rose and partially melted. As this crust moved away from ridges, it cooled, thickened, and increased in density. Eventually, some portions descended back into the mantle along subduction zones, carrying surface materials downward. This circulation transferred heat from deep interior regions to the surface efficiently and continuously. It also established a long-term recycling system linking crust, ocean, and mantle. With tectonic cycling came increasing differentiation of the crust. Continental fragments composed of lighter, silica-rich rocks resisted subduction more effectively than denser oceanic crust. These buoyant blocks accumulated through accretion and collision, gradually assembling stable continental nuclei. Such cratons, once formed, persisted for hundreds of millions to billions of years. Their stability provided enduring surfaces upon which sediment could accumulate and landscapes could evolve without constant obliteration. As the planet cooled further, volcanic intensity moderated in frequency and scale, though it never ceased. Magmatic processes continued to shape topography and influence atmospheric composition, yet catastrophic global resurfacing events became rare. Instead, geological change operated through localized or regional processes. Erosion sculpted mountains, rivers transported sediment, coastlines shifted gradually rather than through complete planetary resets. The reduction in internal heat also influenced the mantle's viscosity. Cooler mantle rock flows more slowly, leading to more defined plate boundaries and less pervasive deformation. This shift reinforced the development of organized tectonic regimes. Over long durations, the interaction of plates generated mountain belts, ocean basins, and complex crustal architecture that would support varied habitats and climatic feedbacks. Surface stability increased alongside internal reorganization. Oceans persisted across vast basins. Continental platforms endured through successive cycles of uplift and subsidence. The atmosphere and hydrosphere interacted with crust in ways that promoted chemical equilibrium rather than constant upheaval. Carbon cycling operated across expanding continental areas, reinforcing climatic moderation. Even as cooling progressed, Earth remained a living planet in a geological sense, its interior active and its surface dynamic. Yet, the intensity of transformation diminished compared to the earliest eons. The planet had learned to dissipate heat through structured mechanisms rather than through episodic catastrophe. Plate tectonics served as both engine and regulator, transferring energy outward while reshaping the surface incrementally. Through this gradual thermal evolution, Earth transitioned from a world dominated by raw heat to one governed by sustained circulation. The cooling interior enabled a stable crust, stable oceans, and persistent tectonic frameworks. It was not a loss of vitality, but a refinement, a shift from tumultuous infancy to mature dynamism. In learning to cool, the planet secured the conditions necessary for long-term continuity and complexity upon its surface. Almost everything from Earth's earliest age has been erased. Continents have been broken and remade, oceans opened and closed, mountains lifted and worn flat. The rocks that once formed the surface of the Hadean have been subducted, metamorphosed, or melted beyond recognition. Yet from that near-total destruction, something astonishingly small endured. In the Jack Hills region of Western Australia, grains of zircon no larger than sand particles have survived for more than 4 billion years. These crystals formed when molten rock cooled and zirconium silicate crystallized within it, locking in chemical signatures from the time of their birth. Zircon is remarkably resilient. Its tightly bonded atomic structure resists chemical alteration and physical weathering, allowing it to persist even as the rocks around it are recycled through multiple tectonic cycles. Within these ancient zircons lies one of the few direct records of the Hadean. Uranium atoms, incorporated into their crystal lattice, slowly decay into lead at a predictable rate. By measuring the ratio of uranium to lead isotopes, scientists can determine the age at which the crystal formed. Some zircons from Jack Hills yield ages approaching 4.4 billion years, placing them within the first few 100 million years after Earth's formation. Age alone, however, tells only part of the story. The isotopic composition of oxygen within these zircons carries additional clues. Variations in oxygen isotope ratios suggest that the magmas from which these crystals formed interacted with liquid water. Such interaction implies that stable surface water may have existed remarkably early, influencing crustal materials before being drawn back into the mantle and remelted. The presence of these isotopic signatures challenges earlier assumptions that the Hadean surface remained entirely molten for extended periods. Other isotopic systems contribute to the reconstruction. Hafnium isotopes preserved in zircons provide insight into the differentiation of the mantle and crust. Ratios of hafnium isotopes reveal whether the magma source was derived from newly formed mantle material or from reprocessed older crust. Some ancient zircons indicate that continental-like crust may have begun forming within the Hadean, only to be later recycled and destroyed. The crystals act as time capsules, recording episodes of crustal evolution that left no intact rock record behind. Because intact Hadean rocks are nearly absent, reconstruction relies on such mineral fragments combined with modeling and indirect evidence from younger formations. By analyzing isotopic systems, mineral inclusions, and trace element chemistry within zircons, scientists infer the temperature of formation, the chemistry of surrounding melts, and even the potential presence of early surface processes. These data points are then integrated with computer simulations of planetary cooling, impact rates, and tectonic dynamics to assemble a coherent narrative. The result is not a complete portrait, but a carefully constrained reconstruction. Each zircon grain offers a fixed reference in time, anchoring hypotheses about oceans, crust formation, and internal differentiation. Through microscopic analysis of these survivors, the broad outlines of the Hadean emerge. We learn that water likely interacted with crust earlier than once thought. That differentiation proceeded rapidly, and that fragments of continental material may have existed amid widespread recycling. What survived from that era is therefore not landscape, but information, encoded in resilient crystals smaller than a fingernail clipping. In their atomic structures, they preserve echoes of conditions billions of years past. From these minute witnesses, assembled with isotopic precision and geological reasoning, the vanished world of the Hadean is reconstructed. The planet's earliest chapter remains largely erased, yet within grains of zircon, its memory persists in crystalline form. There were moments in Earth's earliest history when survival balanced on a razor-thin margin. Each large impact carried with it an infusion of energy capable of reshaping oceans, vaporizing crust, and transforming atmosphere. To understand how fragile habitability may have been, researchers turn to numerical models that estimate the thermal and environmental consequences of collisions during the Hadean and early Archean. When an object several tens to hundreds of kilometers across strikes a planet at high velocity, the kinetic energy released is immense. Upon impact, that energy converts into heat, shock waves, and excavation of material. Rock can be melted or even vaporized locally and eject a blanket vast regions. In extreme scenarios, oceans may be driven to boil globally, and surface temperatures may rise beyond the tolerance of most known organisms. Impact sterilization models attempt to calculate the energy required to eliminate all microbial life, both at the surface and within protected niches. These models consider not only peak temperatures, but also depth of heat penetration. Surface sterilization is comparatively straightforward. High temperature and ultraviolet radiation can eliminate exposed organisms quickly. The deeper question concerns subsurface habitats and deep ocean environments. Heat must conduct downward through rock and water, and that process occurs over time. Simulations show that while massive impacts can raise global surface temperatures to extreme levels, complete sterilization of organisms several kilometers below ground would require exceptionally large bodies, perhaps comparable in scale to the largest impacts known from later geological periods. Energy thresholds, therefore, become critical. There exists a range of impact sizes that would devastate surface ecosystems, yet leave deeper refuges intact. Only impacts exceeding a certain magnitude, releasing energy sufficient to raise temperatures at depth beyond biological tolerance, could eliminate life entirely. Estimates suggest that such sterilizing events were possible but infrequent even during heavy bombardment phases. The distribution of impactor sizes follows a steep decline toward larger bodies, meaning that the most catastrophic collisions were rare. Timing also matters. As the frequency of large impacts decreased over time, intervals between severe events lengthened. If life emerged early, it may have faced repeated disturbances but also enjoyed periods of recovery. Microbial populations can rebound rapidly compared to geological timescales. Even if surface conditions were periodically reset, protected communities in subsurface or deep marine environments could repopulate newly habitable regions once temperatures declined and oceans recondensed. The concept of a narrow survival window arises from this interplay between destruction and refuge. Too many large impacts in rapid succession could have prevented sustained establishment of life, repeatedly erasing nascent ecosystems before they gained resilience. Too few impacts, and delivery of water and organic materials might have been limited. Earth's history appears to have occupied a middle ground, violent yet not continuously sterilizing, harsh yet intermittently permissive. Models incorporate uncertainties in impact frequency, ocean depth, crustal thickness, and early biological tolerance. Modern extremophiles demonstrate that life can endure temperatures and pressures once thought prohibitive, suggesting that survival thresholds may be broader than early estimates assumed. Nevertheless, the margin between survivable and sterilizing conditions was likely slim during certain intervals. Earth did not avoid danger by a wide buffer. Rather, it navigated a sequence of probabilistic outcomes shaped by impact statistics and planetary physics. The fact that life persisted implies that total sterilization thresholds were rarely exceeded after the earliest, most chaotic phases. Within that constrained window, chemistry progressed to biology, and biology endured despite recurrent shocks. The planet's capacity to host life depended not on the absence of catastrophe, but on the rarity of impacts powerful enough to erase every refuge at once. It is tempting to imagine that life required calm from the beginning, that tranquility must precede complexity. Yet the earliest chapter of Earth tells a different story. The same forces that rendered the young planet hostile also shaped the conditions that made habitability possible. Within extremes of heat, bombardment, and tectonic unrest, opportunities emerged that quieter worlds might never have offered. Chaos, at a chemical level, does not mean disorder alone. It means flux, gradients, and the constant rearrangement of matter. Repeated impacts fractured crust, exposing fresh mineral surfaces to ocean and atmosphere. These newly exposed rocks participated in reactions that altered seawater chemistry, releasing ions and trace elements into circulation. Shock waves generated high-pressure environments capable of synthesizing complex molecules from simpler precursors. Even as collisions vaporized water and remelted crust, they also delivered raw materials from space, including volatile compounds and organic molecules embedded within carbon-rich meteorites. Each impactor carried fragments of the early solar system. Within certain meteorites are amino acids and diverse organic compounds formed in interstellar clouds or within parent asteroids. During periods of frequent bombardment, such materials would have accumulated on Earth's surface. Although some were destroyed by heat upon entry, others survived, mixing into oceans and sediments. Water itself may have been supplemented through these arrivals, augmenting reservoirs generated internally by volcanic degassing. Volcanism, persistent and widespread, played its own constructive role. Outgassing supplied carbon dioxide, nitrogen, sulfur compounds, and water vapor to the atmosphere. Beneath the surface, magma interacting with seawater drove hydrothermal circulation, establishing environments rich in chemical gradients and dissolved metals. These systems recycled nutrients continuously, preventing stagnation and maintaining dynamic chemistry. While eruptions could blanket regions in lava or ash, they also renewed the crust and fueled energy pathways independent of sunlight. Recycling extended beyond volcanism into tectonic motion. As fragments of crust thickened and moved, materials were drawn downward and reintroduced through melting and eruption. Carbon, sulfur, and other elements cycled between interior and surface, preventing permanent sequestration. This geological metabolism maintained planetary disequilibrium, a condition favorable for chemical evolution. Life depends upon energy flow and gradients. A perfectly static planet would offer few such opportunities. The paradox lies in the interplay between destruction and creation. Impacts capable of boiling oceans also fractured rock and delivered organics. Volcanic outpourings that sterilized regions also released gases essential for climate stability and nutrient availability. Tectonic forces that deformed crust also created varied habitats and sustained long-term recycling. Violence, rather than opposing habitability outright, contributed to the very processes that sustained it. A world free of collisions and internal heat might have cooled too quickly, locking volatile compounds within minerals and halting chemical innovation. Conversely, a world subjected to continuous global sterilization would never permit complexity to persist. Earth's history appears to occupy a middle path. Catastrophe occurred often enough to stimulate chemical diversity and redistribute materials, yet not so relentlessly as to prevent recovery and continuity. Within this balance, chemistry matured. Molecules assembled, reacted, and in some sheltered niches began to replicate. Life did not arise despite the planet's turmoil, but within it, shaped by the flows of heat, matter, and energy that defined the Hadean and early Archean. What once seemed purely infernal reveals itself as generative. The forces that scorched and shattered the young Earth also laid down the pathways through which biology could emerge, turning apparent hostility into a foundation for persistence. After ages defined by impact scars and molten horizons, a quieter rhythm took hold. The planet did not fall silent, yet its violence no longer set the dominant tempo. Heat still rose from the interior, Continents still shifted, volcanoes still breathed into the sky, but the scale of upheaval diminished into patterns that could endure. Earth was learning steadiness. Cooling continued, imperceptible from one generation of rock to the next, yet profound across eons. The mantle convected with more measured motion, and crust thickened into plates capable of sustaining lasting boundaries. Ocean basins settled into persistent forms rather than transient depressions. Water cycled reliably between sea and atmosphere, condensing into clouds and returning as rain without being repeatedly driven into global vapor by impact shock. Shorelines stabilized long enough for sediments to stack in orderly layers, preserving quiet records of tides, currents, and climate. The oceans themselves became reservoirs not only of water but of continuity. Their depths buffered temperature extremes, absorbing heat and redistributing it through slow circulation. Chemical exchanges between rock and seawater approached dynamic equilibrium. Dissolved elements found recurring pathways through weathering, deposition, and tectonic recycling. This long-term balance reduced the severity of environmental swings and fostered sustained habitats across varied settings. Life, already present in microbial form, persisted within this emerging stability. In hydrothermal systems, within sediments, across shallow marine platforms, communities adapted to local conditions rather than to constant planetary resets. Metabolic pathways refined through incremental selection. Genetic variation accumulated over vast spans, guided by ecological niches that now endured long enough for evolution to proceed without perpetual interruption. Though invisible to the naked eye, these early biospheres transformed chemistry molecule by molecule. Oxygen remained scarce in the atmosphere, yet biological activity increasingly shaped planetary processes. Organic carbon burial, sulfur cycling, and localized oxygen production began to influence geochemical gradients. Over time, these interactions would culminate in profound atmospheric change, but for now they unfolded gradually beneath an anoxic sky. The groundwork for future transformation was being laid in silence. The stability achieved during this transition did not erase danger entirely. Impacts still occurred, climates still fluctuated, and tectonic forces continued to mold the crust. Yet none of these forces returned the planet to its former inferno. Instead, they operated within a framework that supported persistence. The interplay between interior heat, surface water, and atmospheric chemistry had found a durable equilibrium. From this equilibrium emerged the foundation for everything that followed. Continents would assemble and break apart. Oceans would open and close. Life would diversify beyond microbial simplicity into complex, multicellular forms. All of those future chapters depended on the cooling that allowed crust to endure, on the oceans that remained liquid, and on the survival of early organisms through the most volatile ages. The quiet after the fire was not an absence of motion, but a refinement of it. Energy continued to flow from Earth's core to its surface and outward into space, yet the extremes softened into sustainable cycles. In that moderated world, chemistry matured into biology, and biology began its long dialogue with geology. The planet that once seemed forged only in destruction had become a stable stage for continuity. The Hadean ended not with an abrupt stillness, but with a deepening memory. Rock preserved records, oceans maintained their presence, life carried forward. From cooling crust and persistent seas arose a world capable of remembering its own beginnings and of nurturing complexity beyond anything imagined in its earliest fires.